We have all felt a laptop charger get uncomfortably hot, or watched a phone dim its screen to keep itself from melting. That everyday annoyance is actually the symptom of a hard physical limit that is threatening the future of computing. To process more data or move more electricity, we have to cram increasing amounts of current into shrinking physical spaces. All that concentrated electrical traffic generates extreme friction, and our current hardware is simply running out of ways to shed the heat. To keep scaling up technology, engineers are looking past traditional metals and silicons to a material that handles thermal stress better than anything else: diamond. Transitioning to renewable energy grids and ultra-fast charging networks requires moving massive amounts of power. That infrastructure will burn itself out if the core components cannot survive the temperatures they create. Silicon has been the workhorse of the electronics industry for 70 years. But as circuit designers compress the most active regions of microprocessors to smaller and smaller sizes, the amount of heat generated per square millimeter is pushing the material to its breaking point. As electrons flow through a silicon chip, they constantly collide with the atoms making up the material. Every microscopic crash releases energy, which quickly builds up as localized heat in the crystal lattice. This diagram illustrates the path heat takes to escape a microprocessor. Engineers operate with a strict thermal budget, a constant allowable temperature drop between the transistor junction, where the heat originates, and the ambient air where it is released. Looking at this chart projecting thermal resistance over time, the problem is clear. The thermal resistance of the chip itself, our chip, represented by the lower red arrow, is rising sharply, moving to intersect the maximal allowable total resistance by the end of the decade. Because silicon naturally traps too much of its own heat, it lacks the thermal capacity to handle the intense high-voltage demands of next-generation power systems. Diamond solves this bottleneck through atomic geometry. Unlike silicon, its atoms lock into a hyper-rigid tetrahedron. Heat moves as microscopic vibrations called phonons. Because the lattice is so stiff, these waves pass straight through without scattering, carrying heat away instantly. High thermal conductivity is only half the equation. Diamond also possesses an ultra-wide bandgap. A bandgap is the amount of energy required to kick an electron loose so it can conduct electricity. Diamond's bandgap is massive, nearly 5 times wider than silicon's, meaning it can block immense tidal waves of voltage without breaking down. By pairing an unbreakable thermal highway with an extreme tolerance for high voltage, diamond achieves a level of durability that makes it virtually immune to electrical failure. There is an engineering paradox here. That perfect locked atomic structure that handles heat so well also means diamond naturally has no free electrons. In its pure state, it is a flawless insulator that won't conduct power at all. To make it function as a semiconductor, researchers perform doping, forcing foreign atoms, like boron, into that tightly packed carbon grid to free up electrons. The success of this process is measured by the Baliga figure of merit. This metric serves as the ultimate scoreboard, grading how efficiently a material conducts electricity when it's on, against how much voltage it can block when it's off. This chart compares specific on resistance against breakdown voltage for various materials. The dark red line at the extreme bottom right is diamond. It easily outperforms gallium nitride and silicon carbide, blocking tens of thousands of volts while maintaining incredibly low electrical resistance. Mastering the doping process for a material with this specific profile removes the thermal constraints that have decaded electronic design for decades. Actually putting this to use requires solving a brutal manufacturing process. Growing electronic-grade synthetic diamond means replicating the crushing pressures of the Earth's mantle, or relying on complex microwave plasma vapor deposition in a lab. Even when the diamond is successfully grown, engineers still struggle to effectively add negative charges, a process called N-type doping. This limitation severely restricts the types of circuits and bipolar devices we can currently build. Then there is the physical issue of scale. This image shows a heterogeneous epitaxial single-crystal diamond substrate measuring just 92 millimeters across. That is a tiny fraction of the size of the massive silicon wafers rolling out of modern foundries. Those extreme production costs and small physical yields dictate that diamond chips will bypass consumer gadgets entirely. The economics only make sense for high-value infrastructure. we will see this material deployed in the heavy machinery of the electric grid. Solid-state transformers handling megawatts of power and high-capacity EV stations charging cars in minutes demand the thermal endurance only diamond provides. In the near term, manufacturers are building hybrid solutions. By bonding thin layers of diamond directly to gallium nitride chips, they are creating composites that balance electrical switching speed with advanced heat extraction. Moving away from fossil fuels means generating, storing, and distributing more electricity than at any point in human history, putting a massive strain on standard hardware. To manage that load, the components themselves have to evolve. Mastering the precise atomic structure of carbon allows us to build electrical systems that shrug off environments that would melt traditional electronics. The everyday problem of a hot device is driving a pressurized engineering race toward an ice-cold, diamond-powered future.